Hello everyone, thank you for joining this seminar. So my name is Céline Comte, I'm a researcher at CNRS in France, and I will be chairing this session. And it's a great pleasure for me to introduce Pascal Moyal, who will be talking in this presentation about stochastic models related to online matching. Many of you may actually already know Pascal, for instance, as the organizer of the 2023 In France APS conference in Nancy, but let me briefly introduce him. Pascal is a full professor in the mathematics department at the Université de Lorraine in Nancy, France, where he's currently the head of the probability and statistics team. He's also an associated researcher at the INRIA PASTA team, where, as I checked, the PASTA is an acronym for the French translation of space-time random processes and applications. His research activity focuses on the stochastic modeling and analysis of networks, and in particular on Markov chain modeling, weak approximations of stochastic processes in large state spaces, and stochastic processes on random graphs. Before joining Université de Lorraine in 2018, he was an associate professor at UT Compiègne in France, and then an invited associate professor for 2 years at the Northwestern University. Pascal, please go ahead.
Thank you very much, Céline, and thank you all for the invitation. It's a great pleasure and honor for me to make this presentation in front of such a nice audience, and to give me the opportunity of presenting so what I hope will be a comprehensive survey of my work of the, let's say, last 7 to 8 years on stochastic matching models, which have been the main topic of my research for the last 7 to 8 years, in particular due to the fact that it was the main topic of a research grant, an ANR French grant I obtained in France in 2018. So I will. So in this talk, I will first give the motivations for introducing such models. I think that most of you know them, but so I will try to introduce a unified settings to characterize, to define and characterize them. To give a few, so I will try to keep the spirit of a survey. So to give a few, let's say now, classical results regarding stability and the representation of the steady state in particular, and then point out 3 apparently disjoint research directions that I have followed recently on this class of models, and I will try to make the presentation as consistent as possible with respect to these various topics. But let's say that the 3 last sections are more or less disjoint, and I will try to give you a glimpse of what I did recently on that class of models. So in order to describe the class of system at hand, I have borrowed the very first, so the figures that Jean Mérès showed in his very first presentation on this class of models, like on our very first draft 10 to 11 years ago. So a bipartite matching model can be viewed as let's say, an extension of a skill-based service system, where you have, let's say, 2 classes of server, so 2 servers actually, and 3 classes of customers. Okay, and there are compatibilities between the servers and the customers, and here the compatibility between classes and of servers and customers, between classes of customers, sorry, and servers, is given by this W graph here. Okay, so bipartite graph that represent the compatibilities, and here it's a service system where the customers enter and leave the system as soon as they are served. So the extension consists in considering that the customers come and go into the system, but also the servers. So if we consider the exact same compatibility structure, but now the servers come into the system, and the system is just used as an interface to put in contact the servers and the customers, and as soon as a couple customer server is formed, the couple leaves the system right away. So there are no service times. So it's not a proper service system. It's just an interface to put in contact servers and customers that belong to various classes that are compatible or not. Okay. So I quote here a few classical references on this class of models. It is so my literature review is not at all exhaustive, and I apologize in advance for that. But so a few references I quote here. So the applications of this class of system is quite so huge. In fact, you can find in any random system where you need to put in contact elements that needs to be paired. Okay, so we have such a kind of model. So we can view organ transplant systems, online dating, job search, public housing allocations, assembled to other systems, and so on. So with respect to the architecture I just showed, so here the graph is bipartite because there are classes of customers here and classes of servers. Okay, so it's natural to have a bipartite graph, and it's the same if we consider supply and demands, organ and receivers, job and applicants, and so on. But in many other applications, we will need the graph, the compatibility graph, to be general, to account a more flexible structure. So this is the case for online dating, for peer-to-peer sharing platforms, for assembled to other systems, or also for kidney cross transplants system. I will come back to that later. So in many cases, we will need the compatibility graph to be general instead of bipartite, so which is a very important feature here. So it's kind of an abstraction of the customer server system, except that we don't have customers and servers anymore. So we just have a graph, items incoming to that graph, and that need the system to match them. So the formal model is the following. So I will choose as a continuous example this very small graph, so called the power graph. Okay, so we assume that items of the various classes in the set of nodes arrive one by one into the system. Okay, and that their class I is drawn following a probability measure on the set of nodes. So at each time point, an item enters the system and its class is drawn independently of everything else following mu. Okay, and so here I will focus on a discrete time model, but the extension to the continuous time setting is quite straightforward by using Poisson processes instead of the discrete skeleton. Okay, so as soon as an element enters the system, it is matched, if possible, with a compatible item, and we will consider that two items are compatible if their classes share an edge in the graph. For instance, one item is not compatible with a 3 item, but it is compatible with a 2 item. Okay. And so whenever an item enters the system, there are two possibilities. Either it finds an element to form a match and they both leave the system right away, or it doesn't find an element to get matched and it is stored in a buffer. And what can happen is that several possible matches are possible. If we assume that the 2 enters the system and there are several 1 items and several 3 items, we need a criterion that determines what is the match of the incoming 2. Okay, so we need what we will call a matching policy, okay, denoted by phi. And don't hesitate to stop me if you have any question, in particular in the definition of the model. So all this is pretty classical, but so the settings are, I know it is, so your comprehension will depend on how it corresponds to the way you have seen it presented in the past. Okay, so the matching policy can be of various types. Okay, so we have, for instance, priority types. So a class 2 prefers a 3 over a 1, for instance. We can have class uniforms types in the sense that I will toss a coin to choose the class of my match if I have several possibility with a uniform draw, say. I can choose to get matched with an item belonging to the longest queue. This is the match the longest policy. And a generalization of this would be a max weight type policy where I will add some weight that corresponds either to a reward or to a cost to this particular match. Okay, and I can also consider a matching policy that take into account the arrival times of the element, like first come first matched or last come first matched, and so on. So following the type of matching policies, the state space of the Markov chain I obtain will be of various types. So if I need to take into account the arriving time, my state would be a word, so a word, let's say W, where the letters from left to right are the classes of the item in line in the chronological order. So W1 is the oldest one in line, for instance, okay? Or if my matching policy depends only on the number of elements of the various classes in the queue, then just a vector having size the number of classes is enough to represent the system in a Markov fashion. Okay, so these are the two main Markov chains, either the buffer detail, which is valued in a larger state space, or the class detail that is just valued in a finite dimensional vector space. Okay, so these are the settings, and to set the panorama, say I will state quite quickly and recall a few stability results on this class of systems that where the geometry of the graph at hand come into play. Okay, so what we call the stability region for a fixed graph and matching policy G and phi is the set of measures, okay, that we denote stab of G phi, that makes the corresponding Markov chain positive recurrence. Okay, so the set of measure mu. So everything depends on mu here. And it can be observed quite immediately that the stability region is necessarily included in the set n-cond of G, which is the following. That is the set of measures such that the measure of any independent set of the graph, that is a set of nodes that doesn't include any pair of neighbors, must be less than the measure of the set of neighbors. So E of I is the set of neighbors of element of I. Why? Because in order for the cardinality of the elements of classes in I to be able to decrease, we need to see as much arrivals of their neighbors, because they cannot form couples within an independent set. Okay, so in fact, to show the result, which is kind of an elementary result, we will use what I will call frequently a law of large number argument. That is, if it was not the case, so for simplicity, I just consider as a converse the strict inequality. So the equality is a bit more involved because we need to deal with null recurrence. But so in the case where mu of I is strictly more than this for some independent set I, it is quite immediate to see that the number of elements of class in I queued in line at time n, I call it Qn of I, must be larger or equal than the number of arrival to I by time n, which I denote an of I, minus the number of matches of element in I, involving element in I by time n, which I call mn of I, which is itself less or equal than the number of arrivals of elements of the neighbors of the set I. So by a simple law of large number argument, you see that if this is true, then this will be strictly positive for large enough n, which will force the queue to grow to infinity. Okay, so this is a very basic observation, but it sets the panorama, let's say, to classify the graphs and the matching policies when it comes to their stability region. So we will say that the graph is stabilizable if it is possible for some matching policy to stabilize it, for some mu and some matching policy to stabilize it. So if stab of G and phi is non-empty. We will say that the policy phi is maximal if its stability region coincides with n-cond. That is, we have also the converse set inclusion. Okay, so the n-cond is the largest possible stability region. So do the two sets coincide? In that case, we say that phi is maximal. And we will say that the graph itself is maximal if it is stabilizable, and any phi is maximal on G. Okay, so whatever the matching policy, the stability region will always coincide to n-cond. So is it often the case that the stability region coincides with n-cond? Here I show a simple example where in the first case it is the case, and in the second case it is not the case. So for policy B, on the power graph. So if 2 prefers 1, then it can be shown by using a Lyapunov argument that the stability region for mu3 equals mu4 is exactly the triangle that is exactly n-cone. Okay. Whereas if I apply the policy A, where 2 prefers 3 and 4 over 1, then the stability region is strictly smaller. This is the gray zone part. Okay, so you can see with this very simple example that in general, the stability region doesn't coincide with n-cone. Another example is that if I apply the class uniform policy for these measures on the power graph and, for instance, on the 5 cycle, okay, it can be shown that the corresponding mu's satisfy n-cone, but they make the system unstable. So class uniform in general is not maximal, meaning that its stability region, which is so in general impossible to determine exactly, or at least we don't have a criterion to determining it exactly. We have shown by ad hoc arguments that rely on so Lyapunov study of the Markov chain and so on, that the stability region does not coincide with n-cone. So to introduce more general results, so let me just list what we obtain over time. So what can be shown is that for a graph to be stabilizable, it is necessary and sufficient that it is non-bipartite. So let me just stress on the fact that for the bipartite matching model that I have mentioned at the very beginning of the talk, the arrivals were pairwise. So at each time there were 1 customer and 1 server arriving in the system. So it's a completely different dynamics. Here we have single arrivals, and in that case, so if the graph is bipartite, the system can never be stable. So in that case, if G is non-bipartite, so n-cone is not empty, any matching policy of the max weight type is maximal on G, and it is the case in particular for match the longest. It can also be shown that for very nice graphs that are called p-partite complete graph that correspond, so to speak, macroscopically to complete graphs, if you want. Okay, so these are graphs so that can be partitioned into p maximal independent set, and all the edges between these independent sets are satisfied. Okay, so in that case, G is maximal because all the matching policies amount to one another. So in particular, they all amount to match the longest, which is maximal. So the graph itself is maximal. Okay, so a question is, so are there other graphs that are less nice and that are maximal, and for which I don't have to bother with the definition of my matching policy and achieve the maximal stability region, whatever the matching policy I choose? So that question, so does the converse hold for some other graphs? And the answer is no. So in fact, so the two are equivalent. We have shown in another paper together with my colleague Ohad Perry, that aside from very particular graphs for which so big graphs for which we conjecture that in fact it works, but we weren't able to prove it, that the only maximal graphs are p-partite complete for p larger than 3. Okay, so the proof is quite involved, but it shows that aside from very particular graphs, for any graph that does not correspond macroscopically to the complete graph, the matching policy matters because you can always find a priority policy in particular, and the class uniform policy never have a stability region that coincide with n-cone. So you always lose something by not applying the right matching policy. So this is an important feature of these results. Any question? Okay. Okay, no. So going forward over time, we also have shown that the matching policy first come first matched is also maximal. That is, for any mu in n-cone, the model is stable. And in fact, in the particular case of first come first matched, it can be shown that the stationary distribution on the set of words has a product form, which is quite nice. So a few remarks about this result. So first, that it is nice because it gives so nice average characteristics of the system in steady state, like the number of elements in the system, the waiting time, the matching rates, which are important elements for optimization of the system. But we need to be careful because in general, so as often for product form result, there is a normalizing constant for the stationary measure, and computing it for a large state space is in general very cumbersome. So it's not always possible to explicitly compute it. Okay. And a third remark is that in an ongoing work with Céline, we actually show by using the strong similarity of this class of systems with order independent queues that a wide variety of first come first match matching models satisfy such product forms. So not only the particular model I present here. So if we have discrete or continuous time systems, they both satisfy the same type of product form result with or without memoryless reneging, finite or infinite buffer, and also for state-dependent arrival rates. That is, if to some extent the arrival rates depend on the state of the system, then we still have this product form as long as we apply the first come first match matching policy. So it's a quite strong matching policy in that sense. Okay, so I quote here another bunch of references on related systems that use compatibility and achieve product forms for the stationary distribution. Okay. And so this is the end of the survey of the first part of results dedicated to stability. And now I will spend some time in drawing a few connections with an apparently disjoint problem, but which is closely related, which is the one of constructing online matching, so performant online matching algorithm on large random graphs. So let me remind you, so in a few words, the very classical problem of the classical marriage problem on graphs. So the marriage problem is so you have a bipartite graph with the same number of elements on both sides, and you need to construct what is called a matching on that graph. That is a subgraph of this graph involving all the nodes and such that each node has degree 0 or 1. And if in your matching all the nodes have degree 1, meaning that they are paired, married with one and only one neighbor, okay? And so by definition, by construction, all these neighbors are different from one another, then you have constructed a perfect matching. So there is a very well known sufficient and necessary condition for the existence of a perfect matching on a graph. And so this is the well-known Holt's condition. And you can see that our end-cone condition is closely related. It's kind of a stochastic counterpart with a strict inequality here of Holt's condition. So what needs to be reminded here is that even though we know that a graph satisfies Holt's condition, if you go greedily and add matchings and add edges to the matchings with no particular criteria, in general, you don't achieve the perfect matching that you could have achieved with a better algorithm. Okay, so here we achieved a coverage of 5/6. Okay, so meaning that we could have been able to match everyone, but in fact, by going greedily, we matched 10 nodes out of 12. Okay, so in general, online matching algorithms fail to achieve the perfect matching. So there is an extension of this, a generalization of this result for general graphs, which is Tutor's theorem, that gives us a necessary and sufficient condition for the existence of a perfect matching on a general graph having an even number of nodes. Okay, so these results, which are classical results in graph theory, concern a static scenario, meaning that we know the graph, so the only work we need to do, randomly or not, is to match the nodes in the most efficient way, okay? Having the graph, knowing the whole graph, okay? But these results don't take into account the necessity that we can have in the applications for matching on-the-fly nodes that construct a graph that is constructed sequentially over time. And this is, in fact, exactly what we do in our stochastic matching model. So another way of viewing exactly the model that I have presented in my introduction is the following. So if we set what we call a root graph, let's say that's the power graph of four nodes, and we construct a graph by adding nodes. Okay, so the arrivals of our items are in fact arrivals of nodes having a label that is 1, 2, 3, or 4. Okay, and we will draw an edge between two elements if and only if their classes are compatible. So let's say I draw a node 1, then I draw a node 2. They are compatible, so I can match them. Then I draw a node 3. It is compatible with 2, but 2 is already matched. I continue. I draw another 3. Then I draw a 4. 4 is compatible with 3, 2, and 3. It can be matched with one of the three nodes. So let's say this one, and so on. Okay, so here I have constructed at time n equals 6 a random graph of size 6. It is random because the labels and therefore the neighborhood of the nodes are random. They are determined by mu, and a matching on this graph together with the construction of the graph itself. Okay, so this is the exact same model that I presented earlier, but viewed as a sequence of random graphs that grow over time together with the matching on them. Okay. I add another node just for pleasure. Okay. Okay. So in fact, what we have defined here in the language of random graph theory is in fact a stochastic block model graph. So a stochastic block model graph is exactly this. So a random graph, okay, with let's say n nodes, where the nodes have labels, so they belong to communities. So let's say we have P communities. In our example, there were 4 communities: the 1, the 2, the 3, and the 4th. And we will assume that independently of everything else, for any 2 pair of nodes of community, let's say I and J, the probability of the existence of an edge between the 2 is Pij, okay, which is a positive probability that only depends on I and J, independently of everything else. Okay, so so this is what is called a stochastic block model. And what is interesting is to observe that, in fact, the graph I have constructed here, if we just forget about the matching for now, is a realization of a particular stochastic block model where, in fact, Pij equals 1 if and only if the edge ij is present in the root graph, and Pij is equal to 0 if and only if the edge is not present in the graph. So for instance, P12 is 1 and P13 is 0. Okay, so it's a particular kind of stochastic block model. Okay, so in fact, what we have shown in another line of work is that we can generalize our stability results so as to construct matchings on the stochastic block model by constructing sequentially a growing sequence of stochastic block model graph, okay, and a matching on them. Okay, so how does it work? So let's start again with the root graph. Okay, so 1, 2, 3, 4. So I draw 1, then I draw 2, and with probability P12, so I have a Bernoulli random variable, I toss a coin, and the edge exists or not. So let's say it exists. Then I draw a 3 with probability P23, there is an edge between 3 and 2, okay? But so so this time I lost, so there is no edge between 3 and 2, and so on. So there is a 3 with probability P23, there is an edge, there is, then a 4, some edges are actualized and some other don't. And this is how I constructed a graph that is included in the graph that I obtained in my former construction, because my Pij's were all equal to 1 whenever I and J shared an edge in the graph. Okay, so this is a way of sequentially constructing a stochastic block model. And I can now, on this sequence of growing random graph, construct a matching exactly following the same procedure as in the stochastic block model. Sorry, exactly as in the stochastic matching model I described in the first section. Meaning that if 1 and 2 share indeed an edge, which is the case here, I match them because they are compatible. 3 was not compatible with anyone at this stage. 3 is compatible with 2, but 2 is already taken by the 1 node. Then 4 comes into play. E shares an edge with this 3, so they can be matched, and so on. So 2 shares an edge with these nodes. It can be matched with this one. I match it, and so on. So this is kind of an efficient way of constructing a stochastic block model and a matching at the same time on this sequence of graph. And in fact, so the only thing I need to specify here is what is the matching criterion. So what will decide the node I will be matched to, if any. Okay, so we apply the following, let's say, pessimistic policy, meaning that, so I will apply kind of a pessimistic version of match the longest, meaning that, so let's say that I draw an incoming node Vn, and let's say it is of community J, okay, so Cj. So I will look into the argmax of the size of the queues of the neighboring nodes, that is, of the nodes that will possibly share an edge with it. Okay, so I will pick the class, and then I will draw the existence of the edges with all these xi elements. Okay, and if one of them shares an edge with the new node, then I will match the two nodes together. But if all of them don't share an edge, then I won't match my new node. And this, even though I could have matched the new node with possibly with another node of another class. So it's a way of simplifying the matching criterion, but it is not optimal because sometimes I don't match a node that I could have matched with other nodes that could have shared edge with it. Okay, so following this simple procedure, it is to be observed that first that the matching for a graph of size n is perfect if and only if the Markov chain that describes just the number of unmatched nodes of all classes is exactly the null vector, okay? And that in fact this Qn sequence is in fact an irreducible DTMC. So in fact, the correspondence between the two problems is as follows. In fact, the matching is perfect on my sequence of graph infinitely often, almost surely, if and only if the DTMC is positive recurrent, okay? Because it comes back to zero, meaning that at that time n, there are no more unmatched nodes, okay? So the result is as follows. So using a quadratic Lyapunov function, it can be shown that the drift is less than the bound I show here, okay, which depends on the minimal of the difference between the mu of E of I and the mu of I. So as a consequence, the CTMC is positive recurrent because it has a negative drift if and only if mu is an element of n-cond, okay? Meaning that, so if eta is strictly positive, almost surely we have a perfect matching infinitely often. That is, it happens infinitely often in time that I have a graph with a perfect matching on it using this procedure. And if to the contrary, n-cond is not satisfied, okay, the matching is almost surely perfect finitely, so a finite number of times, okay. We also obtain by, so classical use of the drift of Lyapunov function, for instance, bounds on the expected number of unmatched nodes at any time, okay. So if I can gather all these observations, we can make the following comments, is that, so first, if mu satisfy n-cond, it is easy to show by the law of large numbers that the sequence of random graph satisfy the strict version of Hall's condition almost surely infinitely often, because of my assumption on n-cond, okay? Also, the corresponding stochastic matching models is stable, so the sequence of random graphs infinitely often admit a perfect matching, okay? Which implies in terms that this sequence of random graphs infinitely often satisfy Tutor's condition. So this is a bit surprising to us, and we don't have any element to let's say to understand it better. It means that, so Tutor's condition, so if I can come back to it quite quickly, so it's a bit involved. So it's a condition that is way more intricate to check than Hall's condition, and it is necessary and sufficient for the existence of a perfect matching. So what we show by using a matching algorithm that is able to achieve a perfect matching infinitely often, is that as a corollary, the graph structure that it implies satisfies the complicated condition of Tutor's theorem, so infinitely often in time. So which is kind of a nice observation to make, and it is just due to the work we have done to stochastic matching models that have this implication on maximal matching on random graphs. Okay, so our current works on this topic involve so most of all the return times to the full matching and the sparse case. So what happens if the Pij scale with n, which is an interesting question in itself. So observe that whenever the Pij don't depend on n, we have exactly an Erdős-Rényi graph, and of course in that case you want to have kind of to be led to some kind of a phase transition for your the existence of a perfect matching, and this is what we are looking for whenever scaling the Pij with the size of the graph. So this is ongoing work. Okay, so another. So let me close this chapter. Let's say to now turn to a completely other view. So I'll be back to the queuing system, okay, and make the following simple observations. So sometimes in real life, in the applications of matching models, we need to take into account the possibility of matching more than one element at a time. Okay, so for instance, if we consider cross kidney transplant, okay, so a general graph is involved because in fact the elements are couples. Okay, so a couple donor recipient where the donor and the recipient are not compatible. Okay, so they need to be matched to another couple donor recipient where the donor 1 will give its kidney to recipient 2, and donor 2 will give its kidney to recipient 1. And then the compatibility, if we just take into account the blood types between couples, is known. So the graph is known, okay? And it's a general graph between couples. So here, it's a graphical model. But now, if we take into account, as is now the case in some US states, it's not yet allowed in France, but it is in the US. So chains, or for instance, of size 3. So we have a chain of 3 couples. So donor 1 gives to recipient 2, donor 2 gives to recipient 3, donor 3 gives to recipient 1. A matching that is now a triplet of transplants is made between 3 elements, okay, where here elements are couples, okay? So the classes of D1R1, D2R2, and D3R3 must belong to a common hyperedge that is to a possible matching by group of 3, okay? So in such cases, we need instead of a graphical structure to match the element, we need a hypergraphical structure that is edges of size more than 2. Okay. Another example where it comes into play is the classical assemble to order architecture, where final products are sets of possibly more than 2 components that compose them. Okay. And that arrive randomly over time in the assemble to order chain. So in all these cases, not only do I need to match 1 with 2, but also with 3 together to form a whole. Okay. So there are a line of papers of various from various perspectives that allow the possibility of matching elements by groups of more than 2. Okay, so I list them here, but it's not exhaustive at all. So the question is how to formalize the settings of my first section to a matching model where the matching structure is a hypergraph instead of a graph. Okay, so as we saw in the second section, there is a close correspondence between between stochastic matching models on graphs and the construction of maximal matchings on a graph. Okay, so or a random graph. So the matching theory, Hall's theorem, and so on. The problem here is that there are no such things as Hall's the simple criteria of Hall's theorem and Tutor's theorem for hypergraphs. So the matching theory on hypergraphs is much less mature and more intricate than on graphs. So it's more complicated. So I will present a list of results that we obtained in an attempt to generalize our theory of matching models on graphs to random graphs. Okay, so for this I need to introduce a few definitions, and you can of course keep them if you're not familiar with that on the slides that you will be able to read after the talk. So an hypergraph of size q has q nodes, and order m means that there are m hyperedges where the hyperedges are subsets of cardinality 2 or more. okay, of V. So, of course, if all the hyperedge are of cardinality 2, we have a graph. So it's a strict generalization of the concept of graph. The rank is the largest size of an hyperedge. The anti-rank is the smallest size of an hyperedge. If the two are equals to R, then the hypergraph is said R uniform, and a graph is a two uniform hypergraph. Okay. Also, the degree of a node is the number of hyperedge it belongs to, and we need also the definition of a transversal of an hypergraph. That's a set of nodes that meets all its hyperedges. So, and the transversal number is the smallest cardinality of a transversal. So there exist transversals. So the smallest one, its cardinality, it's called the transversal number of the hypergraph. So, for instance, if we have a graph and it is a star, okay, so the transversal number is 1 because there is one node intersecting all the edges, for instance. Okay. So I give as an example, so the complete 3 uniform hypergraph of order 4, meaning that we have 4 nodes and all the nodes are exactly of, all the hyperedges are of cardinality 3. And in action, this is exactly the same matching model as the one on graph, meaning that my item enter one at a time, and I will gather them by groups of 3 as soon as I get them, right? So 2, 3, and 4, I put them together because I have the complete graph, okay? 1, 2, and 3, I put them together. 1, 3, and 4, I put them together, and so on. Okay, so this is the exact same dynamics, except that the matching architecture is a hypergraph. So I will go quite quickly in listing the results. You will have the occasion to read them in more details in my slides. So in fact, we obtained a list of quite disjoint results as that generalize to some extent the result we obtain for graphs. So if you want to have the equivalent of enconde for hypergraphs, so in fact, the closer we can find to enconde are these sets of measures, okay, that deal with independent sets in some intricate way, okay? What can be shown is that the stability region is included in the intersection of these two sets, and the proof is, and most of the proofs of this part, in fact, all rely on the same law of large number argument, okay? Except that, so the probabilistic part is kind of elementary, if I may say. But to prove that the condition holds, in fact, we need sometimes some quite involved combinatorial argument on hypergraphs, okay? And in fact, the natural question is what happens in the case where the hypergraph is a graph, so the rank is equal to 2. In fact, our necessary condition is weaker. So in the sense that it is larger, so more specifically, enconde for the hypergraph, if the hypergraph is a graph, is in general strictly included in this set, the intersection of these two sets. Okay, so then I can present you very quickly another list of necessary conditions. So the stability region is included in a set that is given by the transversal number of the graph and also by 2 other sets. So we have kind of 5 enconde sets, and STAB is included in the intersection of these 5 sets. These 2 sets deal with the anti-rank of the hypergraph, and it can be shown that the stability region needs to be included in that. And once again, most of the proof are combinatorial here. So the probabilistic argument is just always the law of large number argument I presented before for graphs. So as a corollary, so now that we have this bunch of 5 necessary conditions, I can put in evidence sets of hypergraphs that are not stabilizable. So for instance, if you have an hypergraph that contains an hyperedge with 2 isolated nodes, it cannot be stabilizable. So it is not stabilizable. If a graph has transversal number 1, so generalizing a star, okay, then it cannot be stabilizable. If my hypergraph contains 2 intersecting hyperedges that each one have at least 1 isolated node, the system is not stabilizable, okay? And in particular, this implies that the dedicated item condition that was present in Itai and Amy's paper granted some of their results is in fact a condition that is, so as soon as it is satisfied, the model is necessarily unstable, but that is implicit in their results. So the correspondence is quite nice. And also, so other results, so I don't list all of them here. Other results involve the equivalent of being bipartite for an hypergraph, and always the same. As a graph was not stabilizable, a bipartite hypergraph is not stabilizable either, and it can be shown the following way. So just a last remark on this. So a quite well-known hypergraph in hypergraphical theory is the so-called Fano plane. Okay, so for three uniform hypergraphs, that's it's well known in projective geometry. So it's known as the only hypergraph for which, so that is three uniform, for which each pair of nodes appear in a single hyperedge, and each pair of hyperedges intersect at a single node. Okay, so it can be shown that the Fano plane for which I just erased one hyperedge, so here I erased the hyperedge 4, 5, 7. So you can check if you add the hyperedge 4, 5, 7 that it is exactly the Fano plane as I defined it, that this model is in fact three uniform bipartite, so it is not stabilizable, for instance. So we have a list of non-stabilizable hypergraphs. The question, which is quite natural at this stage, is is it possible to stabilize at least one model on a hypergraph? So does there exist one stabilizable hypergraph? And the answer is yes. Okay, we have put in evidence at least two. Okay, so a three uniform hypergraph that is complete three uniform of order at least 4 is stabilizable. It can be shown by using an auxiliary planar Markov chain and Lyapunov argument on the plane. Okay, and also a bit more involved model is complete three uniform hypergraphs of order at least 5. Okay, where we delete a disjunct set of hyperedges. This one is stabilizable also, meaning that we were able to define a set of measures that can make the system stable for much the longest. Okay, and here the proof is horrible actually. So we needed to adapt Lyapunov argument to the embedded Markov chain at times that are multiple of 4. Okay, so we need to find the right scale, if you want, and apply Lyapunov argument to that embedded chain to obtain the result. Okay. So I will just now spend my last 5 minutes or so to give you another. So if you are interested in viewing more in details this list of results of stabilizability or not for hypergraphs, I will be happy to discuss it offline. I will now turn to a very last research direction that we have followed in the last couple of years. Is an element for coupling from the past for the general stochastic matching model. So I come back now to the general stochastic matching model on a graph, okay? And as I observed earlier, we sometimes have the stability region, okay, or at least have an idea of the stability region, but in general, we don't have any clue of what is the stationary distribution of the model. And even in the first come, first matched case, we have the product form, but in general, the computation of the normalizing constant is complicated. So having exact estimate of the various characteristics at equilibrium is far from reach. Okay, so in that cases, there are two solutions. Either you can approximate the system, and there is a very active line of research which I won't mention today on fluid approximation of this class of model to have estimate for the characteristics of the model at equilibrium. But another way of tackling the problem is to try to efficiently and simulate it at equilibrium. So this is the so-called perfect simulation algorithm. And so it is well known that coupling from the past algorithms is a fruitful tool in this context. So what is the idea of coupling from the past? Is that, so if you assume that the Markov chain you consider has a finite state space, it consists in setting all the versions of your Markov chain with the same random input, okay? So the different versions are all the versions of the chain for all the possible initial values. So far away in the past, so that they will all have merged. So all the trajectories will have merged by time 0. Okay. So here and then we say that we have coalescence in the past. Okay. So here the coalescence time is -7. Okay. And the strength of this construction is that at any time earlier than -7, so -8, -9, and so on, the trajectories will remain merged. And in that case, it can be shown that the value that is produced by these merged trajectories at time 0 is produced exactly from the stationary distribution of the Markov chain. Okay. Whereas if you merge forward, that is, if you do the exact same work by setting all the different values at time 0 and wait for them to merge forward in time, then this property is not conserved anymore, and the value you produce at time 7 here is in general not produced by the stationary distribution. So backwards coupling is stronger than forwards coupling. Okay. So this is the theoretical result. The problem is that in general, so CFTP algorithms, so coupling from the past algorithm, are very prohibitively hard to implement if the state space is large. Okay, so one will typically look for good algebraical properties of the Markov chain in order to just simulate a few trajectories to be able to capture the coalescence time. So this is easy to do in the case where it's a DTMC, not a CTMC. Sorry about that. So when the DTMC is monotone, it's doable also applying envelope techniques or bounding chains in some cases. But in our case, so in a matching model, none of this good algebraical property is satisfied. So in fact, we came up with a nice algebraic property that has shown to be efficient in that respect, and this is sub-additivity in that case. So what we have shown is that matching models are sub-additive in the sense that if you concatene two scenarios of arrivals and you consider the number of queued elements, okay, this number is never larger than the number of queued elements if you split the two parts of the arrival scenario, meaning that merging the arrival scenarios, okay, never does worse than just the number you have added, okay? So we have shown that most matching policies satisfy this property, okay? But in fact, it is not a free property, so not all of them check that property. It can be shown that match the shortest does not satisfy the sub-additivity property. So here I have concatenated the two scenarios of arrivals. Okay, in the first case where they were split, the number of unmatched items was 2. Okay, only these two ones. If now I put them together, okay, the number of unmatched items is 4. So we don't have this subadditive property, and when you don't have it, like it's to some extent, chaos can propagate in the sense that if you concatene arrivals on the left, so towards the past, it can make the situation worse, more than linearly worse, if you want. Okay, whereas you can check that applying match the longest to the exact same scenario, you don't encounter the same problem. Okay. So what we obtained is that in order to apply, so let me just turn to that. This is the last step of my construction. We were able to design an efficient perfect simulation algorithm by using first the subadditivity property and the existence of what we call 2C strong erasing world in the particular case, sorry, where the buffer is finite. So I need to make my state space finite. So I assume that my buffer is finite and has a size 2C, okay? In that case, if there exists a combinatorial so let's say object that we call a 2C strong erasing word, that is a scenario of arrival of length 2C that is able to erase any existing buffer, okay, then we can implement a very simple perfect simulation algorithm. So we just need to ground the existence of such 2C strong erasing word, and we have shown that they exist in various contexts. So for non-bipartite graph, for last come first match, many graphs under first come first match, and so on and so forth. And until this condition, the theorem is as follows. So suppose that there exist 2C strong erasing words and the matching policy is sub-additive. Okay, so in that case, we are able to control what we add to the trajectories when we go further and further in the past. We are able to show that if we see as an arrival scenario a 2C strong erasing word, then all the trajectories coincide, they merge. So we have the coalescence in the past, and so we have an efficient perfect simulation algorithm, which I detail here. So it is not useful to keep track of all the trajectories, which was the combinatorial cost of keeping track of all the trajectories. It is huge if the state space is large. Okay, we just need to keep track of the arrivals, and as soon as we see a strong erasing word, and it exists, so it will, by a geometric argument, it will happen someday. Okay, as soon as we see it, then all the trajectories set at any possible values in the pact will have coalesced by that time, and we only need then to simulate a single trajectory up to time 0 to have a realization of the stationary distribution. So it's a very simple algorithm that has shown to be much more efficient than the brute force coupling from the past algorithm, and that is able to that allowed us to compute by Monte Carlo simulations so many characteristics at equilibrium by just simulating a bunch of realizations of the steady state by perfect simulation. We also did the same not for finite buffer system, but for a system with constant reneging with kind of similar arguments. So for instance, we are able to assess the loss probability for a system with reneging to compare first come first match, which for a constant patience amounts to earliest deadline first. So the loss probability is estimated at this value with respect to the loss probability that you can obtain, for instance, for match the longest, which is slightly higher. Okay. So these two results are gathered in these two publications for the sub-additivity and finite buffer systems for the first one, and systems with reneging in the second one. And last, I just wanted to quote a few related papers that deal with comparison of matching algorithms in various respects. So for greedy or not matching algorithms in many references, but in particular in the one I quote here, and some other references deal with systems with reneging, as we just considered in my last slide, and I quote some of them here. I will stop here. Thank you very much for your attention.
Thank you very much, Pascal. So do we have any questions in the audience? I see a few virtual applause as I am speaking, by the way.
Thank you.
I think while everyone is thinking, I can maybe already ask one question. So I already asked you a lot of questions online on various occasions, but I had maybe one in particular about the second part of your presentation, the online matching one. So I was wondering if intuitively, do you think that this policy that you look at, like the max weight policy, do you think it would still work if the online graph that you build were like a small world type of graph, with typical nodes that have a more heavy-tailed degree distribution?
Yes, so the construction wouldn't work because it's not at all the same kind of procedure. So in fact, I'm involved in a few related works to that question for assessing the competitive ratio of matching algorithms on random graphs. And as soon as you lose the stochastic block structure, the argument fails. Okay, so you need other arguments. And so along so for such systems, you need some kind of local limit argument to be able to so to track your matching size. Okay, so here let me add also that in the existing works on online matching on random graphs, not exactly the same characteristics are investigated. So what you typically want is, in average, what is the competitive, so the proportion of nodes that you are able to match in average in the long run. So what we obtain is slightly different, is an ability to achieve a perfect one infinitely often. Okay, but it is harder to assess what is the margin of error we have in average between 2 visits to 0, and this is why we are investigating this now, but it is more complicated, let's say, than in the usual, so in the existing works based on local limits, because on local limits you can use arguments that we don't have here. So my answer is, so unfortunately for graphs such as small world or preferential attachments and so on, so these techniques don't seem to fit, unfortunately.
But from what I understand of what you say, like the proof technique doesn't seem to work, but there may still be a chance that the policy itself performs
yes,
reasonably well.
Okay.
I think so. The thing is that
I don't know how to prove such argument, because to some extent you will need to have, so what we need to have is an equivalence in distribution between having constructed the graph beforehand and then constructing the matching on it with our stochastic matching model. Okay, this holds for the SBM. So similarly, you can show that such procedures work for the configuration model, for instance, but for any other type of graphs, I think it will be more disputable. So I don't know how the proof will work.
Okay, thank you. Are there other questions?
Yes, could I ask questions, Sergey Fus? Thank you, Pascal, for this. You put a lot of topics here, you discussed a lot of topics. That's why I remember the last one. So you put a very strong condition, actually, on this, which kills everything, 2K length stuff. For the perfect simulation ideas, you have this extra condition that you have this 2K whatever stuff which kills everything.
Yes.
And you know what I mean,
Yes.
Could it be weakened, like we had in the past, this like renovating type stuff?
So the thing is that we have worked hard. So in fact, it's still an ongoing work to try to fit to the condition you have worked on to have the coalescence time being I forgot the term. So for us to be able to determine it almost surely, that is, you cannot bound it, but you can know where it occurs. Okay, and this condition may hold in general for systems with that are of infinite state space. But in fact, so we couldn't make it to work in our case. So we didn't find the argument right to make it work. So that's why we eventually needed to restrict our study to the case, so to have a proper and practical perfect simulation algorithm to force our state space to be finite. So another possibility is to bound. So to consider a system with reneging, bounding the reneging, and then it more or less amounts to bounding a queue with impatient tasks by an infinite server queue, and then you have the same property. But aside from these two cases, we didn't make it to construct a checkable, that is a well-formed perfect simulation algorithm, aside from the case of a finite state space. But so in real life, everything is finite. So, so we were pretty satisfied with it. But yeah, it was a bit frustrating. I agree.
Yeah, I agree. No, essentially, so you're just in your algorithm, you just wait geometric number, not geometric.
Yes.
Okay,
Yes.
Yeah, step and the backward, go backward and go forward. That's it. Yeah.
Yes. Yeah.
So what we do is that you go backwards long enough in order for you to see once an arrival scenario in a dictionary that satisfies this condition of being a 2C erasing world.
Yeah.
And
So
this word synchronizes all the trajectories.
Yeah, you can do easily. So you consider 2k times geometric number of steps. It's upper bound, which is enough. Yeah.
Yes, it's an upper bound of the number of
which is enough.
need.
Yeah. Okay. Yeah.
Which is enough. But having a tighter estimate of how long we need to wait is an open question.
Okay. Thank you. Thank you.
Any more questions? No, I think that's it. Thank you very much, Pascal, again for the presentation.
Thank you. Thank you all for attending, and hope to see you soon.
Yeah. Have a nice day.
Thank you.
Thank you. You too. Good night.